So what we have seen is that there are many ways to create a parallel computer. And depending on the main architecture, it is either easy or very difficult to program. Perhaps the data flow machines are the easiest to program, and systolic arrays the most difficult. But that depends, of course, on the algorithm. But to take any algorithm and map it to a systolic array is not so trivial, because the compute nodes only can communicate with their nearest neighbors. So either easy to program or high performance, and none of these two is sufficient in a commercial world, because then it must be sufficiently fast and sufficiently easy to program. In the 1980s, multiprocessors with cache memories were becoming commercial products. They were typically based on a single bus, and how many CPUs can be and memory modules can be connected to a single bus. Well, it depends on the application. I mean, if a single bus is the common medium of communication, so if there are too many memory accesses at the same time, then it will be the bottleneck. And it depends on the application how many there are. Note, the cache memories, of course, reduce the number of operations on the bus. But this is very complex, because if the CPUs have cache misses, then they need to use the bus. Okay, so a more advanced so-called topology is needed to make a large-scale shared memory multiprocessor. One approach is called a mesh, and you can think of it as a chessboard where each square has a CPU and a part of the memory, and they can communicate with their neighbors. I mean, they can send messages to the neighbors, but a CPU can address any the verb address can request any address in the memory, and I mean at any square on this chessboard, and then the messages will propagate to that part of the machine, and then the data will propagate back to that CPU. So it's not that they only can talk to the neighbor, but they can address any part of the memory. And this is an acceptable topology, because typically in a single communication link will not be overloaded. Okay, so one question is, what should we do with memory in the cache? Should we tell the others to remove their copy when we modify our copy, or should we give the new value to those which have a copy? We will look into that later, but as it turned out, it's better to tell the others to remove their copy. And the reason for that is that otherwise there is a big risk that CPUs which no longer are interested in something get updates about something that they are not bothered about. Well, they are bothered about the updates, but not the data. They are not interested. So it's better to remove the other copies. But how can we know who has a copy of a cache block of some data? Well, it's called a directory, and at in a node, if we again consider the machine as a chessboard, then each square or node has, as I mentioned, part of the memory and a CPU. And with that, in that node, there is also a directory, which is a memory which tells the node who has a copy of a certain part of memory. So when somebody wants to remove the other copies, it can send a message and ask the directory to check who has a copy, and then there will be messages sent to those who have a copy, which will remove it. Okay, this will be explained in detail at the later lecture, but the important thing is that the machine keeps track of who has a copy, and each memory address has a home location, which can be found using some bits of the address, which will point to, some bits can be used to find out which memory node that address is located in. Okay. A completely different approach still to make a shared memory multiprocessor is to skip the main memory in some sense, namely to use something called a cache-only memory architecture. The idea is that instead of having a fixed or static home location of a variable, the address, which memory node contains the certain variable at a certain time can change. So if we have two threads in different nodes and they access some data in a third node, in a normal cache-coherent multiprocessor, then there will be 3 nodes involved in communicating. But it would be much better if the machine realizes that, okay, it's these 2 nodes which are interested in this variable. So let's move that variable's home location to one of these 2 nodes. And yeah, that's the idea. The point then is to avoid having 3 nodes, which make it slower to when there are several nodes which want to read and modify a certain variable. There was one commercial product for this at from Boston. It's called Kendall Square Research. Kendall Square is it's a square in Boston, not far from MIT. And it can be seen here as well. Okay, and the other machine was a project at the Swedish Institute of Computer Science. So in these 2 machines, there was a competition between these, and actually none of them became commercial successes, but the data diffusion machine was a very interesting research project. Okay, and actually several of the persons involved became top engineers in Silicon Valley, creating some very high-end parallel machines from Sun Microsystems. The main designer of the DDM is now a professor in Uppsala, Erik Hagersten. Okay, so which is the best way to create a shared memory multiprocessor? With cache-only memory architecture or with a more traditional approach? Well, it's impossible to say because it depends on which application. It's really annoying to get the cache misses which cause long delays, and DDM and KSR1, they could avoid that, but on the other hand they are somewhat more complex to produce. Okay, so we will leave it as that. So, summary. What can we learn from the past? Firstly, the difficulty of increasing the clock rate makes chip companies to want us to use multi-core everywhere. Okay? To be a commercial success means it must be easily programmable and sufficiently fast. Okay, perhaps not so many people will actually design a new computer and have to think about this, but most will have to, well, I don't know how many, but many will have to decide on which computer will they bet that it is still around, I mean the same programming model, in many years ahead. So that's the key question. Should we try to get a machine which is as general and standard as possible and expect the program to be able to be recompiled and benefit from a newer version? Or should a project or product or something instead focus on getting specialized hardware which can at the time reach better performance and then need to be rewritten when that hardware is obsolete, the company that produces it goes bankrupt, or something else? That's of course there is no general answer to that. It's just that we must think about that at the point when we decide on which hardware architecture should be something should be implemented on. Okay, and as we saw, Amdahl's law is extremely important, and cache-coherent shared memory multiprocessors, they are here now, and we can, if we want performance, we need if we want performance in our Java, C or C++ programs or other languages, then we must understand how to exploit this kind of machine as well as possible. Okay, and it's also really important to understand that there have been really a huge number of fancy ideas for decades, but we should be skeptical when somebody tells us that they have the ultimate solution to make a faster machine which is easy to program, because it's not, usually. Okay, GPUs are interesting. They are simmed machines with multiple threads, and they work very well for some application types, but not at all for others. At the later lecture, we will look at something called accelerators, which are additions to normal shared memory multiprocessors for a specific application. And the interesting thing then is that it is possible to include it as a part of the machine, so that this accelerator can access memory, can access variables. So it's just like a newer version of this machine. So it's easier to program, instead of having to copy data via the operating system to some external hardware and then copy it back after it has computed something. Okay, so let's wait with that until mostly the end of the course.